Okay, welcome back to electrolytes. We just introduced the concept of electrolytes as things that dissociate, not merely dissolve, but dissociate in solution to produce ions. So now let us continue our discussion of electrolytes, strong and weak and so on. So that gives us strong electrolytes, weak electrolytes, and non-electrolytes. A strong electrolyte is any ionic compound that completely dissociates when it enters solution. Any ionic compound is going to be a strong electrolyte. Doesn't matter if it's soluble or insoluble, it's going to enter solution a bit. And when it does, it will completely dissociate. So sodium chloride is nicely soluble. Let's go ahead and make that clear. It is soluble, so it is a strong electrolyte. It's a strong electrolyte. Let's say magnesium hydroxide is insoluble. It does not dissolve well. It dissolves only like a very, very small amount, like 10 to the negative 12th. Okay, but it is still a strong electrolyte because it produces a lot of ions in solution, even for the small amount that it does dissolve. So just to make that more clear, when you throw a handful of magnesium hydroxide into water, almost all of it will just fall down to the bottom, stay solid. Only a tiny fraction will enter solution, but all of it that does enter solution will dissociate. 100% dissociation for the tiny fraction that dissolves. Okay. That's one of the reasons it's helpful to separate dissolution and dissociation. Now we look at a weak electrolyte. A weak electrolyte is something that only dissociates a little bit, so it doesn't conduct electricity well. And by that, I mean something like ammonia. Okay. Ammonia, it is perfectly soluble in water, but when you dissolve it in water, it produces NH4 plus and OH minus, but not 100%. Similarly, you have acetic acid. HAC is another way of writing that. It's a little bit faster than HC2H3O2. When you put it into water, it will produce H plus and AC minus, the acetate ion. Okay. But this is not 100% for either of them. These are both weak electrolytes, because it is not 100% dissociation. They both dissolve perfectly well, but they don't dissociate perfectly well. Okay? Or they both don't ionize. Okay, so dissociation for this guy, ionization for ammonium hydroxide. Because that's not actually dissociation. Okay, an association is when people come together and they organize. A dissociation would be them separating. Ammonia technically doesn't dissociate. It doesn't break apart into anything. It's just ionizing. It's forming ions in solution. Technically, water's the thing dissociating there. All right, and finally we have non-electrolytes. They don't dissociate at all. They don't break apart. So even though they dissolve in solution, they don't conduct electricity. Next, strong acids and bases versus weak acids and bases. I've already shown a few of these and hinted a little bit at why they are strong or weak. A strong acid is any acid where if you dissolve it in solution, it will dissociate or ionize completely. Hydrochloric acid, hydrobromic acid, hydroiodic acid, basically all of the halogens except fluorine make nice, strong acids. Okay, they dissociate 100% in solution. HCl breaks apart completely to H plus and Cl minus. HBr completely H plus Br minus. Okay? But some polyatomic ions are also nice, strong acids. Nitric acid, sulfuric acid, chloric acid, and perchloric acid are also strong acids. I should say sulfuric acid is the odd one out because it has multiple protons, multiple acidic protons. Hydrogen sulfate 1-. It is also an acid, but it's a weak acid. The first proton is a strong acid. The second proton is a weak acid. Okay. Let me go ahead and write that out. H2SO4 goes to H plus HSO4 minus. Okay, 100%. then HSO4 minus going to H plus plus SO4 2 minus is like 1%. It's a weak acid. Okay? So strong acid dissociates completely or ionizes completely. A weak acid does not. Sometimes you'll hear phosphoric acid, H3PO4, talked about as if it were a strong acid. It does produce very, very acidic solutions, but none of the phosphoric acid protons, none of those 3 protons is a strong acid. Instead, phosphoric acid is really acidic because it has a lot of protons. That's all. So it has a lot of protons to lose. So it's not really a strong acid. We shouldn't talk about it that way. Sometimes I might slip up and talk about it as if it were a strong acid just because that's the way I've been thinking about it for so long. But it is not one of these 100% dissociation acids. Okay? And those are the 7 you need to remember. I haven't yet come up with any sort of fun and winning mnemonic like Brinkelhoff for these guys. You'll just have to find a way to remember those 7. Strong bases, the ones that reliably produce 100% of their hydroxides in solution, are first off the alkali hydroxides, that first column on the periodic table. They are nice and perfectly soluble in water, so the basic versions, the hydroxides, are also perfectly soluble in water, and they dissociate perfectly as well. The heavy alkaline hydroxides, calcium, strontium, and barium, are also strong bases, but magnesium and beryllium are not. Magnesium hydroxide is a weak base. Beryllium hydroxide is also a weak base. They don't count. So here is a flowchart for trying to remember whether it is a strong electrolyte or a weak electrolyte. Is it an ionic compound or a molecular compound? Okay, so we're starting here in the upper left-hand corner, ionic versus molecular. If it's an ionic compound, it's going to be a strong electrolyte. Okay. If it's molecular, we go down to the middle on the left-hand side, and we say, is it an acid, is it a base, or is it neither? If it's a base, then it's going to be a weak electrolyte. So that allows us to differentiate the bases, say ammonia or any of the organic bases, from the ionic bases. The alkali hydroxides, the alkaline hydroxides, even, transition or post-transition metal hydroxides. Okay? Those are all ionic compounds, therefore they're all going to be strong electrolytes. But whether they're strong bases or weak bases, that doesn't matter. Okay? If it's ionic, if it's an ionic base, then it's a strong electrolyte, whether it's a strong base or a weak base. Okay? But if it's a molecular base, a covalent compound, like ammonia, then it's going to be a weak electrolyte. It will also be a weak base. If it's neither an acid nor a base, if it's sugar or carbon dioxide, then it's going to be a non-electrolyte. Okay? It doesn't produce any charges in solution. Okay? If it's an acid, then you have to ask, is it a strong acid or a weak acid? Because a strong acid will dissociate 100%, and it will therefore be a nice strong electrolyte. Okay, so hydrochloric acid, nitric acid, sulfuric acid, those are going to be nice, strong acids. But a weak acid does not dissociate completely. So a weak acid is a weak electrolyte. So hydrofluoric acid, acetic acid, those guys are weak acids. They're weak electrolytes because they don't produce many ions in solution. That is a nice, handy flowchart. Hopefully it will help you to remember. If you're not visual in this way, maybe you can come up with another way to remember it. I don't particularly mind. Just try to come up with some way to remember that ionic compounds are always strong electrolytes. Molecular bases are always weak electrolytes. Molecular compounds that are neither acids nor bases are non-electrolytes. Strong acids are strong electrolytes. Weak acids are weak electrolytes. Hopefully that will be easy to remember. Just remember to separate those two. Acids, you have to consider strong acid versus weak acid, but base, you have to consider ionic versus molecular base. Not strong base versus weak base, ionic versus molecular. That's just one of those inversions that you occasionally encounter with chemistry, and it'll screw with you. You're just going to have to find a way to remember. And that does it for this particular set of slides. I just want to go ahead and reiterate one last time, going to the previous slide, that a strong acid is any acid that dissociates or ionizes completely in solution, and a weak acid is any acid that does not dissociate or ionize completely in solution. But a strong base is always going to be one of those ionic bases, but it is going to be a particular set of ionic bases. Just the alkali and the heavy alkaline hydroxides are going to be strong bases. Every other base, ionic or molecular, is going to be a weak base. So that gives us 7 strong acids and 8 strong bases. The strong bases are a little bit easier to remember, I think, because they come from those 2 columns on the periodic table. Okay, the first 2 columns, bring that up. So the alkali and the alkali hydroxides and the heavy alkaline earth. So that might be easier for you to remember. You nicely visual like that. The strong acids, not so much easy to remember. It's these 3 halides, then sulfuric acid, nitric acid, and then chloric and perchloric. So plenty of oxygens on the chlorine. Okay. So I don't know if there's a nice, easy way to remember that for those visual learners out there. Maybe you can come up with something. But that will do it for this particular set of slides, and we'll be back for our next set of slides in our next video.